Hi everyone, Tudor here. Welcome to yet another online CompSoc STMU. Quite soon after the last one, in fact, but the truth is we found two speakers that were so cool that we just had to bring them to you. We couldn't wait. So here we are. First of all, we're going to have Zotian Tatum of OPTIVER. She will talk about some challenges in data engineering. Obviously, OPTIVER, one of our favorite sponsors, needless to say. And then moving on, we're going to have, in fact, we're privileged to have Lin Min To of MIT and the Nanyang Technological University of Singapore. He will talk about forecasting energy demand using some deep learning, so basically a neural network, in fact. I should mention that he is in Singapore right now, and it's just past 2 a.m. So let's all just take a moment to appreciate that and appreciate his efforts. Yeah, I don't really need to say anything more. I think that's everyone can appreciate that sort of dedication and commitment. So yeah, as I said, first of all, I'd like to welcome Zotian of OPTIVER for her talk.
Hi, everyone. My name is Zotian Tatum. I'm from OPTIVER, living in Amsterdam. Tonight, I would like to discuss with you a bit more about OPTIVER and what we do, and also my role at OPTIVER and the data engineering challenges we face. So let me start sharing the screen. So before we start the main talk, please allow me to first introduce myself a bit. So I was born and raised in China. I studied in the United States, majored in computer science, bioengineering, and minored in dance. So after graduation, I joined Microsoft as a software development engineer, working in the Microsoft Office suite. Then in 2011, I moved to the Netherlands. First, started as a scientific programmer at Department of Human Genetics in a medical center. This is where I was bitten by the big data bug. I was doing data analysis, statistical analysis for genomic data, where we have to handle, at that point, still big gigabytes of data. Clearly, at that point, the data was too big for the biologists to handle. We have to build data pipelines for it and using a computer cluster. And after that, in 2015, I joined at OPTIVER first as a trading performance analyst, looking at our particularly trading performance data, but quickly became the team lead of the infrastructure data team, and has been in this position since then. So for today, I would give you an introduction to OPTIVER and particularly about what we do as market makers. We would like to discuss a bit more on the role of technology in electronic trading, as well as the data engineering challenges for low latency trading. In particular, we're looking into how we do time-stamped network data and what are the challenges facing for capture that. So OPTIVER is a market-making firm, and that was founded on the floor of Amsterdam's European Options Exchange nearly 35 years ago. And in fact, next week is OPTIVER's 35 years birthday. As market makers, we provide liquidity to financial markets using our own capital at our own risk, and by trading a wide range of financial products on exchanges around the world. So today, we are a leading technology-driven tech trading firm with more than 1,300 employees from over 50 countries, working together in our offices in Amsterdam, Chicago, Sydney, Shanghai, London, and to cover the global markets 24 hours a day and ensure we never miss opportunity. So our traders and engineers work very closely together, not just in the office, but also across the offices. to build trading strategies and improve the market, to ensure, and we share our knowledge to ensure that we're always on top in one of the most competitive environment there is. So now I realize that market making is a term that not many people are familiar with, or at least it was certainly unknown to me, and may I say to most of my colleagues before we started working at OPTIVER. So very briefly, market makers are electronic trading firms that use quantitative algorithms and technology to trade financial products on stock exchanges around the world. What makes market makers different from our other trading firms is that we're officially contracted by the exchanges to provide liquidity on their platforms. This in practice means that we have agreements in place with the exchanges to remain present on the market at all times, regardless of market conditions. It also means that we always show both buy and sell prices for products we trade, making it possible for other investors to trade at any given time. So some may wonder, why does the world still need market makers? Think about two scenarios. First one is when the market is very quiet and buyers and sellers may not be present on the market at the same time. Since we're always there with both buy and sell prices, we can trade with these sporadic activities, narrow the buy-sell price spread, and then make the market more efficient. So another scenario is when the market is very volatile, such as the recent market reactions to the pandemic or to the GameStop. So when many participants, such as the pension fund managers and the individual contributors, want to either exit or enter the market at the same time on a volatile day, they can, because we're there to be the partner of these trades. So in this case, we help to ease the volatility and keep the market stable. So we operate in a highly competitive environment. The move from the physical trading floor to the electronic trading platforms has transformed the industry. Traders today are like the autopilot of today, whose main job is to watch the auto trading system or to watch the autopilot system. So what does it make to be a successful market maker? There are two aspects we focus on. First is price. Is how well can we price our financial instruments, and how can we provide the best price on the market? We have a small army of researchers and analysts with their mathematical formulas to figure that out. The second one is speed. So speed has always been important for market makers. Even in the old days of open outcry on the trading pit, as shown on the left, speed means that you are the fastest one to calculate the numbers in your head and shout it out. Today, it means that our trading algorithms has to be the fastest one to calculate the new price and send it out on the wire. So how fast does it need to be? It depends on how often the price changes. So here I'm showing some numbers so that you can have a sense of the activities from a modern electronic trading platform. So the numbers are from Eurex, the largest European futures and options market. This is on a normal day before the pandemic. So for OPTIVER, we subscribe to 125,000 instruments, and for that 125,000 instruments, we received 2 billion price changes during the day, and on top of that, we received 230,000 public trade confirmations, and about 10% of those trades are coming from us. To handle this much of information, technology is crucial for our business success. Technology is in everything we do, and actually there's one interesting fact that we have more engineers than traders. So there are many aspects of our business that have questions about price and speed. And here are some examples. Which trading strategy is winning and by how much? Where is the next business opportunity where we can provide the best price and still be fast and competitive? Are we complying with our regulations in terms of our price? Did an exchange upgrade, sometimes a purely technical change on the exchange side, did it increase or decrease the fairness of the market? At OPTIVER, we aim to make data-driven decisions. To answer these questions, we first need to collect the data, and that's where my team comes in. As the infrastructure data team, we provide this data with network capture. So how do we do it? We have our servers co-located at the exchange, at the data center near exchange, or sometimes in the same data center with a direct network connection to the exchange. We replicate all network traffic from and to exchange to OPTIVER. We timestamp each network packet at ingress with nanosecond precision timestamps. We aggregate them to a single stream of output. That single stream of output is then forwarded to a capture device for persistence. Then the data is forwarded to our data processing pipeline, where we do data deduplication, normalization, and compression. We then store the compressed data into a time series database that's particularly built for financial data. Then we provide the C++ and Python APIs for program use, as well a GUI interface for our user to access. So that's, in a nutshell, what we do. So what are the challenges of setting up such a system? The first one is the volume of the data. So how much data do we capture on a daily basis? And here the numbers actually a bit out of date at this moment. We, in general, let's say last year, on average, we captured 15 terabytes of network data per day. And this year, the average is leaning towards 20 terabytes per day. From there, we, after the data processing pipelines, we have about 3 terabytes of data. And about 70% of that, we persist them indefinitely. So, to sustain the real-time data pipeline, we run into some network bandwidth issues. So, which the first step we did was to actually design a dedicated data transport network alongside our trading network to be able to transport this data back to Amsterdam. The data is not just big, but also very bursty. So the biggest moment that happens every day, very predictably, but is a consistent pattern, is that this is the 10 seconds right after U.S. market open, which is at 8:30 at the U.S. East Coast time or 3:30 at the local Amsterdam time. During that 10 seconds, we capture 35 million packets across the globe per second across the globe. This is a very different kind of behavior compared to general internet traffic. So our system has to ensure 100% capacity at the burst, which also means that 90% of the time, our system is only using 10% of the resources. But we have to cater to the need for that 10 seconds, because that 10 seconds is also the most interesting part of a trading day. The second engineering challenge we have for our capture system is the quality of the data. In particular, the accuracy and the precision of the data. At OPTIVER, we say every nanosecond counts, and we really mean it. In certain scenarios, when we try to improve the performance of our trading systems, it really comes down to a handful of nanoseconds. And if you want to accurately measure that improvement, it means that your measurement devices need to have the accuracy below a single nanosecond. But before we dive below the nanosecond, let me stop you here and think about how long is 1 nanosecond. So a blink of human eye is about 200 milliseconds. And that's where in UI design, they would say that anything refreshed below 200 milliseconds will not be noticed by users. So for Hummingbird, to beat its wings once, it takes 12 milliseconds. So that's much faster, but that's still far away from a nanosecond. So now imagine that you stand right underneath Eiffel Tower, look up, and you look the tip of the light, the tip of the tower, and the light travel from that tip of the tower to your eye takes about 1,000 nanoseconds, so 1 microsecond. So that's still 1,000 times longer than 1 single nanosecond. From the network devices perspective, 1 nanosecond is about 20 centimeters of a cable, of this fiber optic cable. So that's how much we're talking about. So now we have a rough idea of how long a nanosecond is. How can you actually capture it? So in this case, I'm not going to give you the technical details, but let's say we have a very reliable vendor that provided a device that's a highly specialized device with FPGA on board to be able to measure times in this accuracy. Of course, the brochure looks good, but we always have to verify it ourselves. So we got a few of devices like this, and we put it in our lab, and we test it. So what do we do is that we, from a server, we generate a single network stream. We put that into a optical splitter, which means that we kind of divert the light into 2 streams, 50-50 each. And then we put those downstreams into 2 ports on this device. And then we measure the timestamps of those 2 network input. What we can see is that, so on the right side, what you see is the difference between the same network packet timestamped by 2 different ports on the device. So there were a few things I think worth mentioning here. So first of all is that you will see that there is a normal distribution between the 2 ports, and that width of that distribution is about 150 picoseconds in this case, which matches very nicely to what they claim to be the 75 picoseconds accuracy of the device. The second thing notice is that there is discrete values of the measurement, and between each of the peaks, that is 15.125 picoseconds, and that is the precision of the device. So far, very much matching with their with what they claim. Also interesting here is that you will see the difference between the 2 ports is actually slightly offset from 0. And that means that there's one port that's on average always a little bit faster than a timestamp the network packet a little bit earlier than the other. This is actually due to the electronic circuits within the device itself that's showing up on the measurement. So the good part is that difference is actually very static, which means that we can measure each port and figure out the difference between them, and then apply a static offset. And then we'll have our ports timestamps all being aligned together. So far, that's a very good device. So it's a huge improvement from our previous setup, which is 3.85 nanosecond precision, which we cannot even see some of our most smallest performance improvements. So with the new setup, we have the measurement device. However, we run into the next issue. It is nice if you can put all your capture into one device, but that's not always the case. In certain co-locations where we have more servers treating activities, we need more than one device. And then once they are distributed into different devices, their timestamps are still comparable. If they disagree, whose time is actually real, air quote, real? What exactly is the current time? So let me first show you how bad it can be if you don't pay attention to that. So this is actually an accidental experiment we did during the time when we migrated some of the devices from the old setup to a new one. So we then basically have a same network packet that's being captured twice by two devices, but the two devices are synchronized to a time server in different ways. So here we see is that the values can be different in 2000 nanoseconds. So telling us that it's crucial if we want to compare, it's crucial to make sure that the time synchronization happens between the devices if we want to compare the timestamps across those devices. So that became the next phase of the project, or challenge, I say, in this area. So how do you synchronize time between devices? So here's a little bit of background. What are the technologies currently there is to do that? So there's the NTP, Network Time Protocol. This is the widely used and oldest protocol for time synchronization. It is used over the internet. You can expect that the devices synchronized with NTP can achieve about 10 to 100 milliseconds of accuracy. So what it does kind of internally basically is that each device can reach multiple time servers on the internet using the round trip time to the different time servers to kind of estimate where the real time is, roughly estimating where the real time is. Because it's over the internet, so your round trip latency can go quite wide. So that's where also you lose the precision. So the next generation of device, or next way of doing time synchronization, is using the PTP protocol, that precision time protocol, and is particularly designed as an improvement over NTP. So it claims that it can achieve sub-microseconds precision, and is used mostly in local area network. So this is where you, rather than rely on multiple masters, multiple time servers, you basically always synchronize to a single master in your local area, and then you use the in this case, there is less jitter in your round trip because there are less devices, there's a more controlled flow of network, therefore you can achieve much better precision of that. And also you use more of a master-slave setup instead of one server contacting multiple masters. So this is where kind of, before we look into the exotic technologies, this is normally what we need. And from a from trading perspective, financial industry, we have a regulation to require that all our servers are synchronized within 20 microseconds. So this is well below that. So from a normal trading perspective, from normal business perspective, this is totally fine. And this is also the technology we use before we start doing network capture. But those all are not good enough for our use case. So the next thing we look into is called PPS. And in this case, PPS stands for pulse per second. And in this case, it's actually not a protocol per se, because the first two are the protocols, which means that you send network packets, and then you do some analysis to the network packet using algorithms internally to find out the true time. Where PPS is actually electronic signal. So it's really a signal that had a width of less than 1 second and has a sharp rising or falling edge that can accurately repeat once per second. And if done right, then you can achieve the sub nanosecond precision. To really achieve that sub nanosecond precision, you have to make sure there's a very, very low jitter on your equipment. And also, because of the electric pulse, that means that the signal degradation is really fast. So you cannot use this in long distance. Normally, you cannot do this more than 100 meters with a 100-meter cable. And when we use this particular signal to make sure that we account for the electric signal delay, we actually measure the cable length that the signal is transmitted on. So that does fit the criteria of sub-nanosecond precision, but it can only be used when our setup is clustered is very close. And it's not always the case that we can do that. So there comes to the next, even more exotic way of looking, doing time synchronization, which is called the white rabbit. So the white rabbit is actually the name of a collaboration project, including CERN and the GSI Helmholtz Center for Heavy Iron Research and other universities. So basically, this is used to synchronize all the lab devices around the Large Hadron Collider. So they also have this need for synchronizing all their devices within nanosecond precision in a long distance, in this case, from 10 to 100 kilometers distance. So internally, basically, they have three important components. First, it uses the PDP protocol for calculating the time delay. On top of that, you use a layer 1 synchronization with synchronous internet to synchronize your physical layer, and then you do the phase measurement of the local clock phase. So then to get to the final sub-nanosecond precision that you need for synchronizing devices together. So this is actually the case where we deployed one of those devices within a data center, where the master node of the white rabbit network was provided by the exchange, where we're the leaf node, our node synchronized with that. And then based on our timestamp data, we can say we were around 1 to 2 nanoseconds synchronized with our devices. So just for completeness, actually, you can also include the GPS as a way of synchronizing time between different locations that's in long distance. For basically, all the GPS satellites have a atomic clock in it, and if your receiver device can see multiple satellites, then you can calculate the precise distance between the satellite and the receiver, and then use that to synchronize the local clock. So with that, if you have, for example, in London and Amsterdam, if both your GPS receivers can see the same set of satellites, then you can synchronize those two receivers within 10 to 25 nanoseconds to UTC. So this is basically are the 5 way of synchronized time between devices. So how do we do it? For our particular experiment or project, let's say the first co-location where we really want to achieve sub-nanosecond precision synchronization, we used the white rabbit network provided by the exchange, where that particular white rabbit network was first synchronized to GPS on their side, and then synchronized to our local white rabbit node on our side. Then we use a PPS. We use the PPS signal to propagate that sharp edge of each second. Then after that, of course, we have a lot more than 2 devices. So a splitter is not enough. We use a specialized low jitter PPS splitter that can split the signal to 16 times. Then after that, we measure the cable length we use from that splitter to all our measurement devices to get the equal length as close as possible, but also use the exact length of the cable to do the offset. Then we get to the measurement device, and on each measurement device, they also equipped with an internal atomic clock, rubidian clock, to track the time progression within that single second to make sure that is as smooth as possible. So with all the 5 steps done, to the end, we were able to synchronize 10 devices with sub-nanoseconds time synchronization achieved for each pair of devices, and a total kind of overall 2 nanoseconds across all 10 devices. So basically, that's what we achieved for that particular project. So each of we have 10 devices that all can synchronize together, and within that, we each device was able to measure the timestamps to be able to measure the time progression in picosecond precision. So that's my talk. So I hope you enjoyed it, and give you a little bit of flavor what we do on the type of data engineering challenges we have. I do have a few more bit of information for you in terms of opportunities at OPTIVER. So we have an early engagement program where in April we have an Insights Day. So that's open now, and you can apply. This is particularly for the first and second year students. For the summer internship, this is for people, for students graduating in 2022. We have both the tech summer internship as trading summer internship. It's 8 weeks long. We pay for everything, flight, apartments, and you have a salary, and then you have a chance to experience the culture of OPTIVER and living in Amsterdam. The application is going to close very soon, so please apply as soon as possible if you're interested. And of course, we have many roles for graduate students. So if you have any questions, please contact our recruiter. And also, good to remind you that we'll be the Hacktober next week. So please, yeah, if you have more questions, you can also find us there. So that is it.
Right. Hello again. Thank you very much, Zotyan. That was so interesting. A deep dive into just data and all those. For me, it was a good refresher on like units of measurement, like all those transformations from nano to pico and so on. Let's just see if we are getting any questions right now from the audience. I'm sure quite a few of them will contact you afterwards, and because about all those details at the end. Let's see. I don't really see any now, but let's just wait for a minute or so.
No problem.
Just, I will ask a question myself then. How long have you been working at OPTIVER?
So a little bit over 5.5 years. Yeah. So I have to say, when I joined OPTIVER, so I didn't have much of the electronic background nor the network background. So as I mentioned before, I studied computer science as well bioengineering. So my work is really focused on the data side. So software, software development, data architecture, also some more statistics. So actually the many topics today I presented, I learned on the job.
Yeah.
Yeah.
So I guess that's a message to people who are doing computer science at Edinburgh and would be interested in something like that. Don't be scared if you don't have experience with all of those other things. You can still make it.
Exactly. Yeah. So it's definitely the fundamentals of how software works, how computer works, understanding kind of not just purely on the kind of software architecture level, but also a bit on the hardware level. Just having broad understanding of different topics through the university education is super important. And then, but you have to build on top of that. You cannot learn those kind of very deep knowledge through university, but rather is learn how to learn. Give you the fundamental to quickly deep dive into topics is super important.
Mm-hmm. Yes, yeah, I definitely I can agree with that. And so it seems like OPTIVER is not just a good working place, but also a good learning place, which
definitely
I think anyone would be interested in. We're all interested in learning. After all, we're students. So
yes.
See.
Learning never stops. Learning never stops at OPTIVER. Always have new challenges. Yeah.
We did get a question from the audience. So with such insane precision needed, these are not my words, but they're probably very precise. What happens if something goes wrong?
Well, I guess defining what went wrong. So for example, it's an interesting one. So when we're using the PDP signals, before we go into the PPS wide rapid network. Once a while, we'll have a network line outage, and then your PDB synchronization is disrupted, and then you lost the contact with the master. What happened is actually you also lost the contact. You lost your context of the leap seconds since UTC. So what you see actually artificially is that the data leap forward 37 seconds. Sorry, leaped backwards 37 seconds.
Oh, yeah.
And then it won't progress until suddenly when you see the real time, and then you adjust. So then if you plot some data, suddenly if you don't pay attention to it, you may start calculating your performance of your software, and then you will see negative performance. So you go faster than light. So, but rather that's basically when there's issues in your time synchronization, with your time capture, what you see is that you have bad data, and then user have to be aware of that and be able to handle that or filter them out in the downstream analysis.
And just one more question. What's one thing you might not expect about working at a high-frequency trading firm?
I guess one thing that's really mentioned is about the learning. Is that you come into the place, I don't know too much about trading at all. And then have a very specialized field in data analysis, and then you find out there's just so much to learn, and then you give the opportunity to learn it as well. So I think that's my my surprise when I joined a company, and then it's still surprising me 5 years later. I do think that in general, let's say the trading firms across the globe, I cannot speak for all of them, but I definitely know that to work in this environment, you need to be able to kind of keep up with the new technology, because things are getting very specialized. So you have a chance to have exposure to them and learn them on the job.
I see. Yeah. Well, I'm a fan of both surprises and learning. So surprises involving learning, that sounds ideal. Looks like that's it from our audience right now. So again, thank you very much for coming today. I really enjoyed your talk. I'm sure everyone else also did. And we hope we'll see you as an OPTIVER at many of our events in the future.
Thank you very much. My pleasure to be here.
Okay, so this was the first part of our event done. Now we're going to be moving on to our research speaker. So please welcome Lin Minh To from Singapore.
Yep, hello. Nice to meet everyone. Let me share my screen. Can everyone see my screen? Yeah, okay. Yeah, I think it works. Yeah, so hello. Today I'm here to talk about predicting energy demand using neural networks and XGBoost. So so the challenge is to basically some background about this. So I'm actually a chemistry major, and I joined this competition with a few of my schoolmates from my university in Singapore because we like data science and we just want to expose ourselves. So for this competition, we were given a data set of energy consumption data from a building, which is about 2 years, and also we're given some temperature data set. So our task is to predict the next energy demand 24 hours in advance, given the current data. So this is a typical time series problem. And for this, yeah, we also wrote an article on towards data science on Medium, where you can find the full solutions, the full details of our solution. So why do you want to predict energy demand? Well, two main reasons. Because if as an energy supplier, if you are not able to supply enough energy, then obviously there's going to be issues on the electrical supply, and there may be blackouts. But also, if you supply too much energy, that's also a loss, because you waste the electricity, but also you need to invest extra cost to convert that electricity into something else and store it. At the same time, if you have too much supply, you can also like damage the power lines. So given all of this, many companies now want to be able to accurately forecast how much energy do people and buildings really need. So yeah, for this, the main metric that we used is mean squared error. It's a typical metric where we just take the error, the deviation from the true energy consumption and the one predicted by the model, and we just take the square and take the average. And the second metric that is very commonly used in time series forecasting is lag. Basically, you want to calculate like how delayed are your predictions. So you want to make sure your lag is 0, so that when you predict a certain value for the energy at this time, that value is really is not delayed by, for example, 1 hour. Then your prediction has little value. Yeah. So okay, just more of a summary of what this is going to be about. So we didn't use some fancy deep learning techniques, right? It's a simple neural network, but a lot of our attention was on visualizing the data and getting the most out of it, which I think is very important in a data science project, rather than throwing like now the hype is transformers, and just throwing transformers at every problem and expecting to get good results. So especially in energy demand forecasting, I think the focus is more on like interpretability, being able to understand why a model makes certain decisions, rather than just getting the best possible performance and just expecting like energy companies to use the models. So all right, now back to the data. So we just plot the data, all of the data, and we saw that that there was this region in the early few months that was particularly low compared to the rest of the data, which we decided to remove it because we suspect that this probably like the building was under renovation or like it just started operations. So obviously we don't want this in our training data, otherwise the model is going to underestimate the future energy consumption. And then if you remember, we also said that we had temperature data from from sensors placed around the building. So we plotted the temperature, and we saw that there is very significant seasonal variations. So we could deduce that this was building somewhere in the North Hemisphere, and there is winter, summer, and the transition months. And you can see that there is also a strong correlation with the energy consumption. And it's especially high during the winter, but also during the summer, there is a small peak at about July and August, right? The red line is the energy. And during the transition seasons, it's of course like varying between the two extremes. So one of the features that we decided to add is like just a simple dummy variable, which is called is season transition or is season winter. So basically, if the time that you're predicting for is winter, then the value of is season winter would be 1. And if it's summer, then that value would be 0. So it tells your model to, what season it is. And that is actually very important to make the right prediction. And the second one is, temperature, we will have some more figures on temperature, but the only data we're given is the time. And the time of the data collection and the energy consumption value itself. So we figured that from this time information, you can extract a lot of patterns from it. So one pattern that we try to see is whether there's a difference between weekdays and weekends. And as you can see here, there is a very significant difference. Right? On the weekends, the energy consumption is very low. And of course, weekends, we take it to be Saturday and Sunday. And also, we can get the public holiday data from like Google. So you can see that during the weekdays, the mean is significantly higher. So we can infer that this is probably an office building or a school building. So again, the features that you can try to use is something like is public holiday or is weekend. That tells a model that if it's going to be a weekend, then you should predict lower values. And next, so you can zoom in onto a daily basis, and you can plot the energy across the day. And we saw that there was a sharp rise from 7 a.m. onwards and sharp drop off after 6 p.m. So this is most likely an office building. And there's also a interesting drop at about 12 p.m., which we presume is because of lunchtime. So two features that we had is whether it's a lunchtime and whether it's working hour. So these are again like just values of 0 or 1. And another analysis we did was a correlation analysis. So for time series data, if you are lucky, then your data will have some correlation across time. And in our case, the correlation was very strong across one day. So you can see that 96 time steps, because the data is in 15-minute intervals. So 96 time steps is 24 hours. There is a very sharp correlation value. And also another high correlation at 1 week intervals. So it makes sense, right? Because this Monday's energy consumption is probably every Monday, probably the office workers do similar activities and the energy consumption tends to be similar. And every Sunday is probably going to be similar as well. So some of the data that you can give the model is the energy 1 week ago, right? From the time that you're trying to predict the energy 1 day ago. And also in time series forecasting, a common feature that people use is differences. So you can take the difference in the energy consumption between 2 days or between 12 hours. And this kind of tells a model like the rate of change in the energy consumption. So that can also be very helpful information for the model. Yep, so now back to some temperature data. So now what we try to do is to map the energy and temperature by themselves without the time information. And okay, it's not very convincing, but there is a quadratic relationship. And we know this because we looked at the literature, and it's been reported before in papers that there is a temperature where humans feel most comfortable. That's about 18 degrees. So when your weather is too hot or too cold, then people are going to need heating or cooling, and that results in extra energy consumption. So one of the features that we used is to take the square of the temperature, and that becomes an input into the model. And also a related feature is to take the product of the temperature and energy. So that's just part of the quadratic equation. And we can see that on the bottom right, the coefficient of correlation is quite strong if you take the square. So this should be quite useful for the model. Yeah, so that's about pretty much. Yeah, we did a lot of visualizations, but these were the most interesting. And so next is processing the data. So there were two main issues with the data. Okay, there was a very big issue with the data, which was that there was a lot of missing values. And another issue is that you need to normalize the data. So for the first problem, if you look at the top right, there the data that was given to us had blanks of about, I think, about a few days at a time. So if you just take the linear interpolation, it looks very ugly, and it doesn't represent the true data distribution. So that's not a good form of data imputation. And so what we instead tried is, okay, maybe we can try forward filling, which is basically like take the data from 24 hours ago and we just replace it. But then it seems to work, but then it doesn't reflect the weekly trend well, because like if you take the missing data from Monday from Sunday, then we know that Sunday is going to have very low energy consumption. So that doesn't reflect the true situation. So in the end, what we did was to just take the data from 1 week ago, because we also saw in the correlation analysis that 1 week periods have very strong correlations. So if it's a Monday, then we take the data from previous Monday. If it's a public holiday, then we take it from the previous nearest weekend. And that, if you can see on the bottom right, it gives a much more natural looking data distribution. And for the temperature, there was also some gaps, because I think they only took the temperature like every 1 hour. So for this, it's all right to just take the linear interpolation, because you can see the data trend is preserved and like the gaps are not too large. So it's fine to just take the linear interpolation. And coming back to normalization, because if we're going to use neural networks, then it's important to scale the values, because you need to make sure that all your features are considered equally by the model. If you don't scale the features, then, for example, you might remember that we took the square of the temperature, and those values are going to be numerically very big. But it doesn't mean that the square is more important than just the original values. Like the network should take all of them equally. So in order to do this, we just scale all the values. For example, we can minus the minimum value and we divide by the range, the maximum minus minimum, and this will make all the features within the range of 0 to 1. So that will ensure that the neural network won't bias certain features over others. And another quite interesting processing we did is that in time series data, you have time information, right? But for example, we can represent months from a number scale of 1 to 12. But this is actually not good, because if you look at December and January, they are actually neighbors, right? But if you put it on a number scale, the network is going to think that December and January are very different. But that's not the case, right? They're both sort of winter months, and they're both they should share similar characteristics. So what you can do is you can do a cosine and sine transformation. Then you map all the data into a 2D space, as you can see on the right. Then your December and January are going to be neighbors. And like every month is separated by the same distance. And that is really helpful to make sure that you're representing the information correctly for the neural network. And you can do this for month, you can do this for hour and minutes. And we did this for all the time information. And then, yep, so now moving on to windowing. Okay, this is just like, you can take certain windows of the historical energy consumption to like give the model information about the rate of change. So you can take 1 hour windows, 5 hour windows, and 12 hour windows. Yeah, this is more of like, there is no fixed rule on what you can take. Yeah, so now moving on to the actual training procedure. So in the competition, they gave us this platform called AutoCAD, but you can just do this with any deep learning library, right? And so if you remember, we had a lot of features that we brainstormed, but maybe not all of them are going to be important. And it's important to single out the truly important ones and to discard the others, because if you have too many columns, that will cause the curse of dimensionality, where you distribute your data across too many columns, and then some of those columns are not going to be important at all, and confuse the model. So what we did was, okay, I mean, you can manually check each of the features and see if it's helpful for the model, like whether it causes the MSE metric to be better or not. But if you have a lot of features, it's a very tedious process. So something that we did was to use this tool called Sharp, which is too much to explain now, but basically it's just a tool that they use some game theory concepts to help you to quantify how important are your features to make the prediction for this model. And in this case, we have to assume that the features are sort of independent and like they don't interact too much, which of course it's not a very good assumption, but we don't have a choice, so we have to make this assumption. And if you see this figure, so okay, brief overview, like we did do some trial and error on like a range of features to see like what is really helpful. And we saw that in time series, you can do some transformations like skew, kurtosis, and range. And those actually are not useful for the model. And we had about 130 features that were left after that process. And we fed all of this into a XGBoost model, which is just a tree-based model. And then we can get the predictions for the next 24 hours of energy consumption. And then we saw that this model is quite good, like it beats the persistence by 44%. So persistence is just a baseline where you predict the same value for, like if you try to predict tomorrow's energy consumption, you just take today's value and you just bring it forward. So it's a very simple baseline, and this model can beat that by 44%. So it's already a very good model. But mainly what we want is to analyze how it used the features. So out of those 130, we can rank the features using this Sharp library. And it tells us that these 20 or 30 features are the most important. So you can see on the right, like for example, the feature like whether it's a working hour, whether it's a weekday, and the days of the week, they're actually very important for the model to make that decision. And so next, when we move on to the neural network, we just focus on the top 30 or 40, and we just try some combinations to get the best metric. And it really saves you a lot of time. So in the end, we settled with 36 features. Yeah, basically all the dummy variables that we described, pretty much all of them turned out to be quite important. The time data was also very important. And lastly, the non-linear features, right? Taking the square of the temperature or the product of the temperature and energy turned out to be very important as well. And now to the neural network. Yeah, I think basically you can do some hyperparameter optimization to get the best architecture. It's a routine process, so I won't spend too much on it. Maybe something interesting was that for this particular problem, 10H activation turned out to be quite useful compared to ReLU activation. Yeah, if it's your first time hearing these terms, I'm sorry, I don't have time to explain, but they're just some different parameters that you can use in your neural network. And usually it's really not that important. But what I would like to focus on is like to analyze the performance of this neural network. So on the bottom right is a scatter plot of the actual energy consumption values and the predicted values. So you can see that in general, the model is very good, right? There's a lot of values along the linear line, but there is a few that the model is under-predicting or over-predicting. So what happened is that if you look at the top left, there is some periods I think that's in the transition season. So that's like between winter and summer, when the weather is, maybe the weather is very erratic, or we're not sure, but the model is very bad. As you can see, there is a very large deviation from the prediction and the actual energy consumption. So that's causing all those points where you overpredict or underpredict. But in general, we calculated the percentage improvement over the persistence, and it's like 53%. So that's a very good start. And also, if you can see the bottom left, for the lag, it's 0. So basically, there is two peak correlation values. One is at 0, and another is at 96, which is basically 1 day apart. So this is expected, right? We know that energy consumption is highly correlated across days, but our model has a higher coefficient at the time difference of 0, which tells us that it's on time, right? It's not delayed by 1 day. Yep, so we can look more into the daily plots, and we see that our predictions are pretty good, especially if you look at the public holidays. The model it knows that for public holidays you should predict less, right? And having the feature like the dummy variable like is public holiday is really helpful for this. And if you look at the green box, it's a regular working week, and you can see the peak and the throws. We would say we were very pleased to see this. But also, if you remember the transition periods, I think that's in February and March. The model is not so good. Sometimes it gets like too high or too low predictions. But also, if you look at this carefully, these days where the model predicted like low values, but actually the energy consumption was very high, are on Saturdays, which you can't really fault the model, because on Saturdays it's supposed to be a holiday, right? People are not supposed to be working, but maybe during those periods there was something else going on in the building, but we don't have that information. So there's some limitations from the data that you can't overcome because you just don't have the data. So yeah, looking back at the model itself, I think for time series forecasting and if you want to use neural networks, it's going to need quite a lot of data. Luckily, we had about 1 year of training data and 4 months of test data. So that turned out to be sufficient. I mean, of course, it's a competition, so they have to make sure there's enough data. But some issues that we should be careful of is that the model was trained on this specific weather, right? So there's geographical constraint, and you shouldn't expect this model to do well in a country like Singapore, where there's no seasons, where it's always hot and wet and hot and wet. This model is not going to do well in that situation. And also, the type of building matters, right? Whether it's a shopping mall or whether it's a school or office building, the patterns across time will be different. And lastly, something that sort of like we didn't have a choice, but using a neural network tends to make things like a black box that you lose the interpretability. So that's why if interpretability was more important, then we might want to use a simpler model like XGBoost, or even an even simpler model where we can really understand how the model is making the predictions. So just to recap, so what we did was we had the final 36 features, and we fitted it on the XGBoost again, and we used the Sharp library to visualize the features. And again, it's pretty much the same as what we got initially. So you can see the time features are one of the top ranked, and also there is the fourth highly ranked one is the product of energy and temperature. So that's quite important as well. And some difference information is also useful for the model. So we hope that maybe if someone wants to do energy consumption forecasting, then these would be useful information. And lastly, this is my last slide. I think just to recap the process, we spend a lot of time on data pre-processing and data visualization to really understand what's happening in the problem. And in fact, the actual model training just took a bit of time. especially because we used the Sharp library to narrow down the features. And it's more important to really understand what's going into your model. And moving forward, okay, this was a year ago, but if we had the chance to work on it some more, then we may try to develop different models for different seasons. For example, that may give you like more specialized models that you can use under different conditions. But of course, you can also throw more advanced architectures like LSTMs and transformers. But then these are also very complex models, and you need a lot of compute power to train these models. So that may not be an option for some businesses. And at the same time, you lose even more of the interpretability with these models. And of course, something that we want to try is to just deploy it on cloud, and like people can just see the model working in real time. Yep, and that's it for my presentation. Yep, thanks for listening. If you want to read our article, please feel free. And you can also add me on LinkedIn to have a chat.
Hello again. Thank you so much, Lynn, for the talk. It was absolutely fascinating to hear you go into all those details of the implementation of like processing the data, then just applying and coming up with all those variables and helper things. It was just amazing to hear you break it all down. Because obviously I looked at the article before, but hearing you talk about it it was just on another level in a way. It's really helpful, and I'm sure quite a lot of others, quite a few of them have also loved it. I have shared the article to the event chat channel on the Discord as well.
Right.
People, just some quick feedback from some of the audience to hear someone predict something so tangible, so practical, basically. So this was for a competition, right?
Yeah. So yeah, like it was quite funny because like all of us were sort of like, we're not experts, right? I'm from a chemistry background, and I had people from like earth science and physics background. So none of us were from computer science. But like we saw this competition that was like sent to us from our university, and we were like, okay, let's just try it. And we just, we took a very scientific approach to the problem, and like that was enough to win the competition.
Yeah, little wonder that one. I can definitely see how your entry could win one of these competitions. How much time did you have for that project? That's another question from the audience.
I think we had 2 weeks from start to end. Like, so there was, they gave us a data set, and then we had 2 weeks to do whatever we wanted, and then we had to submit a slide deck, and of course like the performance of the model, and then we had a presentation, a final round and a presentation to explain the model.
Yeah, that's brilliant. The fact that you managed to put all that together within 2 weeks and just present it so professionally as well, because I don't know, everything was just so nice.
Right.
And again, people saying that you had so many good ideas and so on. It looks like people have thoroughly enjoyed this. However, I don't necessarily want to keep you for much longer, since I know it's extremely late and this has already been a bit of a stretch for you. So again, thank you so much for coming. I know I appreciate it a lot, and I enjoyed it so much, and I'm sure the others did as well.
And my pleasure.
Yeah, it was definitely a pleasure to have you. So thank you again.
Yeah.
So that was that. That was the final talk of today's event. Thanks everyone for coming. Hope you enjoyed it. I definitely enjoyed presenting it, as always. And just the final piece of news: in about 4 or 5 weeks' time, we will have the CompSoc AGM. I think most of you probably know what that is. It's basically a bigger event where we host the annual elections for a new committee. So someone will get the opportunity to replace me and do this thing in the future, as just one of the few things that are going to be happening on that event. But yeah, all jokes aside, we're going to have the AGM soon, so please keep an eye on our channels, so our website, our Facebook page, our Discord. We're going to be sharing more updates on that as soon as we're able to provide them after we've arranged all the details. So hope you've enjoyed this, and see you at the general elections for the next event. Thank you.